Good morning, mathematicians. Hope you're doing well. We have crossed the 8K barrier. We are now 8K plus subs. That was fast. That went pretty fast. So earlier this year, I before I took a break from doing office hours, I remember saying like, oh, maybe we'll pass the 10K before the end of the year. And then I took a break and I was like, oh, it's not going to happen now. But now I'm looking at that, I'm like, could happen. I think a lot of it has to do with my Vixra video. And usually, Leo Lectures tried streaming. Nice. And how did it go? What was your stream about? But yeah, so I mean, I don't know if I'm gonna have another video pop off like that before the end of the year. All the videos I'm planning to make don't do that well, like my recent group extensions video. But they're the ones that I want to make, so I'm gonna stick with it. But I'll probably make one more Vixra video by the end of the year. Maybe that will help. Oh, nice. Oh, okay. So you're doing math office hours as well. Cool. Do you have other like long form content as well? That probably helps. Can I go to channel? Oh, I see. Nice. Got some ZFC set theory going on. Axiom of choice isn't controversial. Hold up. Maybe I'll have to watch this later. Hard disagree. Cool. Well, welcome to the math tuber gang. Okay, so the plan for today is I'm going to start reading this paper by some people that I know. I'm going to take a look. And I'm going to try to understand it. And I actually mentioned to one of them that I was probably going to read through this paper on live stream. So they may see this and they may find out how poorly my brain works sometimes. Although, ironically, you don't like measure theory stuff because it feels all just bookkeeping. Is that ironic though? To check that sets are measurable is not very meaningful. Well, yeah. Yeah. But is that really directly related to choice? I mean, choice gives you non-measurable sets, but that doesn't mean that you get measurable sets without choice. Or just by, rather, it doesn't mean you get measurable sets just from ignoring choice. Without AOC, you can have a reasonable ZF axiom where all sets are measurable, but you would need another axiom though, right? It wouldn't just be ZF, because if you just drop if you just drop AOC, all that tells you is now you can't prove the existence of measurable sets, but you also still can't prove, sorry, of unmeasurable sets, but you still can't prove that every set is measurable. Because if you could, then once you added in AOC, if AOC was consistent, then you would have a contradiction. Good morning, Jeffrey Lee. Good morning. Going to watch the semi-direct product videos, hopefully learn a thing or two. I hope so as well. Hello, Bill. Of course you can ask questions here. That's what we're all about. You're working on some real analysis and you're stuck on one of the problems. So definitely you can ask it. I will not promise that I will answer or can answer, but I might try. I might try to answer your question. We'll see. But go ahead and ask. ConZF actually shows this. Sorry, what is ConZF? Constructive? ZF is consistent? Okay, I mean, that's a belief. That's a faith. It's you can't prove that. So LM is just all sets are Lebesgue measurable. Yeah, but what do you mean by ConZF? Constructive. Oh. You're saying that if ZF is consistent, if ZF is consistent, then ZFC is consistent. Yes, I agree. I agree with that. Yeah, absolutely. And similarly, okay, I see what you're saying. Yes. I could believe that. Oh, sorry, you were saying con ZF means ZF. Yeah. Okay, sorry. Hello. Andrea, the FPP conjecture, well, actually, it's technically not arithmetic geometry. We are about to get into, we're going to read about it in a second. At least that's the plan for today. But there is a real analysis question here. Show that for all real numbers, there exists a real number such that x cubed is equal, that y cubed is equal to x. Well, this smells like homework, which doesn't mean. I mean, you say it is from somewhere. Probably you're right. I'll take your word for it. But let me ask you this. In order to solve this problem, well, have you seen a similar thing like this before? For example, have you seen the proof that you can of defining exponents of real numbers? Or have you seen the proof that square roots exist in the real numbers? Square roots of positive numbers exist in the real numbers. So that's my first question to you, because that is going to help help me cater my hint to you based on what you've seen. or if you've seen, or if you've seen in their lecture, they showed root 2 is in R. You're trying to use that technique. Okay, great. So that is exactly what you should be doing. And so what is that? But setting the bounds was a bit hard. So what was the technique? What was the technique that you used? Can you tell me what that technique was? Okay. Well, you type up what that technique was. We'll start reading about the FPP conjecture. So this is for p-adic groups, inspired by the Archimedean case. So K is a local field of characteristic 0. So think the real numbers or the complex numbers. And G is the K points of a connected reductive algebraic group. So you can think GLN, for example, or your favorite matrix groups. It was a triple axle into Pierrette. I think that was a joke in response to something I said, but I'm not sure. I'm not sure, sorry. And so, okay, classic problem in representation theory. We want to let this denote the set of equivalence classes of irreducible unitary G representations, and we want to classify the set. So Adams, Miller, and Vogel propose the FPP conjecture, which posits a strong upper bound on here. Okay, let's jump back to Bill Bogo's question. Yes, exactly. So we want to use Dedekind cuts, right? I mean, that's basically how we define real numbers, is Dedekind cuts. So, so we had, in order to form the square root, we looked at the set of all rational numbers. Oh, wait, maybe you're not doing Dedekind cuts. You said the set of real numbers. I see, right, because we just want to construct it, so we don't necessarily need to make it rational. That is accurate, right? So what do we do? So it's so we can form the set S of real numbers such that, well, we wanted to, there's two parts. We want such that either x is, well, actually, if we're just doing the least upper bound thing, yeah, I guess we can do x such that x squared is less than 2. We could even take it less than or equal to as well. It's just we don't know if the equal is satisfied. Yeah. And so, well, there's you're right that it's that its upper bound has to be root 2. But actually, have you already defined what it means to take square roots in the real numbers, though? Have you already defined the process of roots? Because it's kind of a weird thing. Like, what does root 2 mean? Like, because, for example, we need to define what it means to take roots. So, and let's see, I'm trying to think, how do we normally define that? Because, like, normally we form, like, well, there's different ways to do it, but for example, you would take the Dedekind cut, which is all rational numbers which are less than 0, or whose square is less than 2, for example. Or to be really general, like this is how we define nth roots of rational numbers. So r to the n, and let's say this is another rational number s, right? Now this is a Dedekind cut. So do you know what a Dedekind cut is? Because otherwise this question's a little bit weird, right? If we don't have a rigorous definition of the roots. So this alpha, this is in root n, for example, the definition of what a Dedekind cut is. What we do is we define the nth root of s, like we define it to be this Dedekind cut. Okay, so you don't know what a Dedekind cut is. Okay, interesting. Is this a course that you're is this a course you're taking, or just a course you're following? I mean, I guess this is trivial if you've already proved the third roots and stuff. Yeah, anyway. Okay, but wait a second. It's not asking to take the third root necessarily. I was getting confused because I was thinking we were performing arithmetic operations. So, yes, Cauchy sequences are better than Dedekind cuts. Right. I see it, Rod. Actually, right. So sorry. Maybe I was overcomplicating this. Actually, perhaps it is easier. So, right. So, all we want to show, for example, in the case of 2, we just want to show that there exists an x which squares to 2, right? So we looked at the set of all x in R where x squared is, well, we could say less than or equal to 2, for example. And then what did you do from here in the course? What did you do from here? So you look at the set, let's call it S. And then how did your argument proceed from there? And we can already start thinking about, well, for the cube, so if we have if I want a cube root of something x, we got to think, what am I going to put in this other set here? But what was the next? You showed that it has a least upper bound since 2 is an upper bound. Yes, exactly. So, right, show it's bounded above, and then 2. Well, there's another important step. You also need to show that S is non-empty. Okay, very easy step, but very important because you can only apply the least upper bound property to non-empty sets that are bounded above. So, right. The upper bound can't square to be anything greater than 2 or less than 2. Yes, I think I agree. Yes. So, well then just by, and this is sort of, spiritually like taking a 2 root of 2. So then what is your guess, Bill, for what we're going to put here? So we want now y cubed to be equal to x. We're trying to find this. So what do you think that we might put here? What's your guess so far? Okay, we're gonna whiplash back to this research paper. Will Bill is typing. So Adams, Miller, Vogel proposed the FPP conjecture. Right. So recall that every irreducible G representation has an infinitesimal character, which is regarded as a W orbit on the dual abstract Cartan. Oh, that's the next step. I see what you mean, Matthew. Yes, right. True, right? Because we want to show that right. We want to show that the real number has to satisfy that. Yeah, can't be greater than, can't be less than. Yes. Right. So our infinitesimal characters are Weyl group orbits on the dual. Oh, also maybe I need to switch to live chat instead of top chat. That's part of the problem. So you show that has least upper bound. Yes, exactly. So that's exactly it. Right? We just want to take the same exact steps, right? So we write down the same thing, and well, what do we need to do next? We need to show that it's bounded above. That would be step one. Well, we could always show that it's non-empty first, right? Show that S is non-empty. That's the easier one. I always think it's good to do the easier one first to warm yourself up. So let me know your thoughts on that. I assume you have a question about that part, but so representation as real infinitesimal character if this W orbit belongs to the canonical real form. See, I'm already blanking on the canonical real form. I guess there's always one that comes with the group, right? This is something to do with like the various forms of the group, right? How to show that the canonical Hopf bundle of a manifold has no holomorphic sections. I don't even know what the canonical Hopf bundle of a manifold is. To be honest. If you think it's better to start with the easier one, why not look at Archimedean FPP first? Well, that's true. That is true, Arad. That is true. Yeah, sorry, I don't have any good references for you. I don't even know what the canonical Hopf bundle is. I didn't know you had a Hopf bundle you could associate to any manifold. Oh, do you just mean like for the actual Hopf vibration? Like the sort of classical, I mean, there's like a couple different things that you could call Hopf vibrations. Sounds like it begs to get Riemann rocked, yeah. Here I am. Riemann rocked you like a hurricane. Yeah. For non-empty, we can say that 0 is in the set. That's true. We could sort of do it, but then what if X is not positive? What if X is not positive? So what are some numbers that you know are definitely smaller than x, right? Because we want to try and be slick about it, right? This sometimes in math you're forced into a case by case argument, but if you don't have to, it's better to do it in one fell swoop. So what are some manipulations we could do to x that definitely creates a smaller number? Well, technically, you're right. Leo lectures. If we're talking about p-adic land, there's no need for negative numbers. So the original FPP conjecture of Adams-Miller-Vogel asserts that if pi is an irreducible unitary G representation with real infinitesimal character, then one of the following holds. Either the so we could do well, let me finish reading this and then I'll jump to your thing, Bill. So the infinitesimal character lambda of pi, regarded as a dominant element of the real dual Cartan, either has I guess this is the root action, so I don't know what to call it, the pairing with each simple co-root is at most 1, or the representation is co-homologically induced, which I'm not super familiar with, but I know it's a thing that exists, from an irreducible representation satisfying the bounds. Oh, okay, so it satisfies 1 or it's induced from something that satisfies 1. Recently proved. Okay. In this paper, we formulate conjecture for the non-Archimedean case. Okay, so Bill, good guess, right? We take x, but the thing is, we want to guarantee that this is less than x, right? And if you expand this out, you'll quickly find that that's not always true in general, right? It doesn't necessarily need to be true. It depends on the x you pick. So not a terrible first guess, but it's not going to work out. So what is some other way that we make a number smaller? We have subtraction. What's the other thing that generally makes a number smaller? The other arithmetic operation. Not subtraction, but another backwards kind of operation. Prove our conjecture in the case when G is a pure rational form, meaning pure inner to quasi-split. Division, right. So what do you think we could divide x by to make it small enough? What's a number we could try dividing x by? It doesn't have to be a very crazy number, I'll tell you that. It's like the simplest non-trivial number you would guess. The proof is conditional on local Langlands, which is still a conjecture in general. However, a result is unconditional in many cases where this is known, including when G is a classical group. To state our conjecture, we recall some preliminaries on the Langlands correspondence. Oh, your first preprint is coming out this week. Nice. I hope to be joining you soon, not with my first preprint, but with my next one, Matthew. So maybe we'll be same day publishing twins. One is like saying lambda's minuscule. I think so. X over 10. Yeah, x over 10. So why not take x over 10, right? Totally works, right? Because now take x over 10, cube it. Well, that is x cubed over 10. And now this will definitely be true. This will be less than, wait a second. Oh gosh. No, wait, what have I done? Uh, oh no, I lied. Oh no, I lied. Wait a second. Bill, I messed up and I misled you. Maybe we do want cases. Maybe we do want cases. Bill, I misled you. I'm so sorry. I thought we could do it in one fell swoop, but now I am realizing the error of my ways. But you know what? Actually, I'm so wrong. I misled you. You were right the whole time. This function is monotonic. It's increasing everywhere. It's increasing everywhere though. So, wait, now I am confused. This is harder. Ah, right. Okay. I think Arad has the right idea. So we want to make sure, we want to get it so that x cubed divided by something is less than n. Is less than x. And so in order to make n big enough, we can use the Archimedean property. To choose such an n. But we want this thing here to be a cube. And so, in fact, but we actually know that this will be true. So we can just use the Archimedean property to grab n, and then you can say, well, actually, I'm going to deal with n over 3. And so now we can argue that x over n should be in our set S, since x over n cubed is x over this, which is less than x, which is what we wanted. There we go. Oh, whose cube is less than x? Oh, that's true too. That's true too. I mean, either way. With monotonic, what is wrong with soup A where A3 is less than x? A rational? I'm not sure I understand the question, Leo Lectures. I'm not sure I understand the question. But yes, I forget what minuscule means. But how are we choosing n? Well, Bill, are you familiar with the Archimedean property? Do you recall what the Archimedean property of the real number says? Oh, yes, Leo Lectures, to define cube root of x, yes. Yeah. I mean, the way I know how to do it is, yeah, basically you'd use that with Dedekind cuts to define it. Okay, so just setting up some notation. We got our irreducible representations. Pi g is the admissible dual? Oh yeah, instead of irreducible, yeah. Well, that is technically true, Bill, though as a pure mathematician, I like to be really precise. So there's various different ways of forming it, of formulating it. So one way, actually, let me get it right. It's good to stick with the technical, precise definition, right? So Archimedean property. For any two positive real numbers, yeah. So, right, to be precise, for all xy in the reals, such that x is less than y, there exists an n in n such that xn is greater than y, right? So this is the Archimedean property. As a consequence, you have the right intuitive idea, which basically says 1 over n can always be as small as needed. But this is the actual formal statement. And so I think it is worthwhile. To understand how to formally go between this statement and derive this result. So I sort of went in steps where I said, so in this case, I'm imagining, x3. Now we have to be a little careful here because there's, this should still hold just as well with equal signs, right? But so in this case, this x here, so maybe I should have written a and b to be less confusing with our example. So in this case, right, what we want is x3 over n less than x, right? So to get it in line with the conclusion here, we multiply both sides by n, and so we see we want it to be our a, right? So either you can take soup where a ranges over reals or rationals, doesn't matter. Yes, that's true. Yes, that's true actually. But there is something I do recall when you're building like what it means to put things to the exponent of a real number. You have to do it in stages. Oh, but that's fine because this is the single integer case, yeah. If x is negative, then wouldn't that be larger? Yeah, maybe I am overcomplicating this. Maybe this had to be cases anyways, so I don't know. Yeah. But let me just finish this train of thought. This still works. Everything I said still works, except okay, maybe we need cases, right? But the point is, setting this up tells us that we want our b to be x, and we want our a to be x3. And so either it is, we want other way around, a to be x and b to be x3. And so this informs us that, either it's the case that x3 is already less than x, in which case we're done, there's nothing to do, or So either this holds already, or we have that x is less than x3, at which point we can apply the Archimedean property to get this. Yeah, wait, I don't think there's any sign issue, because like either this is true and then the proof goes through, or this is true, in which case you can Archimedean property to get that this is true, and then this follows. Hello, Lockheed SR-71 Blackbird. I've never had a fighter jet join the stream before. Well, happy to have you lurking in the shadows, and glad that you tuned in today. Okay. So, whiplashing. I hope you guys enjoy this whiplash between recent research in the P-adic local Langlands program and real analysis. So we got our Galois group. We're going to take our V group, and our L group will just be, technically not a fighter jet, just a jet. Okay. I mean, I saw Lockheed and Blackbird, and I assumed it sounded like a, yeah. I don't know my jets, it turns out. If x3 is less than or equal to x, how does this show that we have an element in our desired set? Well, I mean, that would show, because what do we need to satisfy to be in our set? We need an element, y cubed. We need some element y cubed that's less than y to be in our set, right? So if x cubed were less than x, then x cubed would be in our set. I was calling it s above, but I guess I should have been calling it t. So we would have that. In this case, we have it automatically. More of a spy plane. Okay. So you're spying on my live streams to collect mathematical secrets. So we've got L parameters, setting notation, L parameters. According to SZ, this is in bijection with G conjugacy classes, where this is a Levy subgroup. Phi naught is tempered, and nu is a positive real valued character of M, which is dominant with respect to P, called the exponent. We can regard nu phi as a dominant element of the dual real Cartan. Aha. Now the real Cartan, we're in the P-adic case. Right, I guess we still have a Cartan. Yeah, we're just taking the Lie algebra of the torus. Yeah. You love spying on branches of math that you don't understand, so you chose to finally tune in today. Cool. Is that enough, Bill, or do you need a little more help with the rest of the proof? I mean, I am going to log off soon anyways. Going to have fun figuring out what the context is here? Well, you can go find this paper on archive, FPP conjecture. From like a week ago. So our infinitesimal character or sometimes infinitesimal parameter, as I call it, will be as such. We can regard this as an L parameter by composing with a projection. And in this way, we can define an exponent of this. Now, here's the p-adic version of the FPP conjecture. Assume that pi is an irreducible unitary G representation, and let phi be, it's enough? Okay, sweet. Well, feel free to come back tomorrow if you want some more gentle nudging towards the direction, towards the right proof, and I will try to not confuse you more. I worry part of my waffling around in different ways might have confused you more. Yeah. Then the exponent of our infinitesimal parameter. Okay, hang on a second. This is interesting. So the exponent in this case really just depends on the infinitesimal character. So if I'm understanding this correctly, this isn't even so much a statement about the unitary representation itself. It's a statement about the infinitesimal parameter. It's saying that, like, if you're an infinitesimal parameter, if you look at the set of representations with that given infinitesimal parameter, if a unitary guy lands inside of you, then you have to satisfy this. Maybe I'm misunderstanding, but that's interesting. I do kind of want to jump over to, Kudla has the, talks about this in his article in the local Langlands correspondence, non-Archimedean local Langlands correspondence, and he classifies, he talks about how to classify the unitary ones with multi-segments. So I kind of want to plug that into here. And here's where we get the FPP part of this from, because this set is called the fundamental parallelepiped. And the conjecture asserts that if pi is unitary, then the exponent of its infinitesimal parameter must belong to this set. The main result is a proof of this conjecture when G is a pure rational form. Okay. Oh, hell yeah. We'll have to see our Kasdan-Lustig hypothesis, baby. Assume that G is a pure rational form and that there exists local Langlands correspondence satisfying the Kasdan-Lustig hypothesis, then this is true. Okay. Well, I think that's where I'm going to leave it for today. Tomorrow, we will dig deeper into this paper, or at least that will be the goal. Perhaps we will have more side conversations about other courses and analysis, and who knows what else. So until then.